Alright then, every challenge question, part 31. It's the vectors, chapter 12 from the book, the last one, I think, aside from the review chapter. Got coordinates here, I'll put them on a 3D grid here, so 1, 3, minus 2. It's difficult to draw 3D coordinates on a 2D piece of paper or screen, but in any case, 1 across, 3 up, and then 2 towards the screen. And I decided to put it across there somewhere, so 1 across, 3 up, and then sort of 2 towards the screen. 1 across, 3 up, and then 4 away from the screen, puts me over there somewhere. And then 7 across is much further along. But before I do that, maybe just connect these 2 points and say, well, okay, the only thing that changed here was going towards into the screen this way rather than back towards me. So therefore, the distance there is just 6, and that's the side of every square. And now I can say, okay, well, here I'm going across 7, down 3, and then back into the screen 4 places there. Well, that's just needs to go across and down from here, right? So that's going across and down from there. Across 6, as Rita said, because it's a cube, and down 6 means that this coordinate here is just 7, 3, 4. And I can just complete this in the same way. So across 6 from here, only changing this coordinate makes 7, 3, minus 2. And then down 6 from here, maybe, takes you, or then down 6 from here takes you to 1, minus 3, minus 2. And then I think down 6 from there takes you to 7, minus 3, minus 2. And then you can connect all these up. I realized I forgot this one in my terrible cube drawing. Down 6 from there, or into the screen 6 from here. Doesn't really matter which way you think about it, I guess. And you're going to get from here 1 minus 3, 4. And you'll get all points of the cube, which is horrendously drawn, but who cares? We're looking for the shortest distance from A to C. So imagine you're walking along the surface of the cube. Like, how would you get from here to here? The obvious thing would be to walk along the front face of this cube and then back along here. But maybe actually going on the top of this cube and then down here is faster. Or maybe it doesn't make a difference. Or maybe even going around the back of it, like down this left side, and then along the bottom is faster. Who knows? Well, what you do to answer these kind of questions is you draw a net of the shape. So what I've done here is I've taken the back of this cube, um, the very back of it. I'm taking that to be the center bit. So the right side folds out here, the left side folds out there, and this top side folds upwards to be here, and then the bottom and the front fold out here. So I'm saying A, because that bit folded upwards, A is therefore this coordinate here. I think in my picture, I could have also said it was this one here, because this left side's moved outwards, and I said that was that one, but it's actually not going to matter, so that's fine. The back side of the cube, I said was here, so C, which is this coordinate down here, must be there, I think, because it's the bottom and the front move downwards there here, so this must be C here. And I just need to work out this straight distance from A to C. Of course, all those distances are 6 across, as I've already said. So of course it's just 12 across 6 up. So Pythag root 12 squared plus 6 squared takes me to 6 root 5. So this question then, we've got a vector minus 2i plus 6j minus 3k. Let's draw the x, y, z axes here. So this is the x, this is the y going upwards, and then the z is going to come in and out of the screen like this. Now this vector goes 2 to the left, which is this way, 6 up, and then 3 out the front of the screen this way here, because it's following the z-axis, 3 that way. And our vector is like this diagonal thing here. Now that vector has length 7, because 2 squared plus 6 squared plus 3 squared is 49. So it's got length 7. And I want to find the angle that vector makes with the xy plane, which you can just imagine as being the screen here, because the z, of course, goes in and out of the screen like this. So the xy plane is just the screen in front of you. So if I draw a vector going from here out to this point here, that's clearly got length root 40, because it's 2 squared plus 6 squared square rooted. And I just want this angle here, I think. So I can just do cos inverse of root 40 over over root 49, or just 7. And I'll get my answer here of 25.4 degrees. Now this question here, we have some amount of this plus some amount of this plus some amount of this equals this. First thing to notice is this middle row. There's nothing here, so therefore r just must be minus 4 to make that work. So you substitute that in, you get this. And now we can just say, if we take away this vector from both sides, we end up with that. So we can say p plus 2q is 8, and 4p minus 3q is 0. This is a simultaneous equation. Times this by 4, I guess. Keep this one on its own. Take them away to get this. Q is this. And then you can figure out that P is that. And we'll be done. This question here then. So we've got... this actually I saw. Maybe it was in a practice paper or an exam paper. I'm not sure. But I did see a question like this before. Using these cubes. And we're going to compare coefficients and come up with some new letters and stuff like that. Anyway, I think I can say that A to F is minus A plus B plus C. O to M is B plus C plus a half A, and B to N, which is the last one that's relevant. B to n is minus b plus a plus a half c. Cool. Now we're going to think about these three lines here. So a to f, o to m, and b to n, the ones that I just got. Now, if I call this intersection here x and this one here y, o to x is therefore some amount of the vector o to m. I'll call that amount k. So it's just some scale amount of o to m because it's along the same place. But o to x is also, I can say a plus some amount of a to f. Some different amount, maybe. Some different amount L of A to F. But of course, these two things represent the same journey. One is just doing this, and one is doing this. It's the same journey, so they must be the same. So a half K equals 1, according to the A's. Sorry, equals 1 minus L, according to the A's. And according to the B's, K equals L. The C's also say the same thing. But of course, this just means a half K equals 1 minus K, which means K is 2/3, I believe, and so is L. And we're done there. So that's cool. So we've shown that this amount is 2/3 of the whole A to F thing, which is quite helpful and good. And now we'll do the same thing for Y. So B to N is some amount, sorry, B to Y is some amount of B to N, so just call it M amount of it. And B to Y is also, I guess, minus B plus A plus some amount of A to F, which is what I've said there. And again, comparing, the A's says M equals 1 minus N. The B's say the same thing, essentially, and the C's say a half m equals n, which is useful. Plug that in there and you'll get m is 2/3, which therefore means that m will be 1/3. And we're all done here because we've shown that n is 1/3, which is the amount of by. So by are described as minus b plus a plus some amount of a to f. That some amount was n. That some amount turns out to be a third of a to f. So therefore, this is a third of a to f. This here, a to x, is 2/3 of a to f. And so therefore this is trisected 1/3, 1/3, 1/3, and we are done here. Last one, I think, says to just find a counterexample whereby if some amount of A plus some amount of B plus some amount of C is equal to some other amount of A plus some other amount of B plus some other amount of C, then those all scale factors are all true. I came up with this one, and I just wrote that one of each of them makes 0, 0, 0, and zero of all of them also makes 0, 0, 0, which means I've satisfied this, but my P, Q, and R are all different to my S, T, and U. So I think that's the counterexample. That is one that works. I'm sure there are lots of them. Anyway, thanks for watching.